Hi there, this is Mr. Pope from Women's Grammar School for Boys. Today, a little bit later today because it's Saturday and I fancy lying, but we're going to be looking at the decision portion of the maths topics I wanted to talk about. So, what is decision mathematics? Well, it's the set of algorithms, instructions, and processes that are kind of closely linked to computing, computer science, if you've got an interest in working with computers, algorithms, how data is sorted, managed, aligned, that kind of thing. We're going to be looking at algorithms, data, graphs, not graphs as in graphs with coordinate axes, stuff like that, but more sets of vertices or nodes, arcs, connecting arcs, minimum spanning tree, building up networks, that kind of thing. Dealing with those kind of problems, two-dimensional, three-dimensional. And then towards the end of this little summer thing, we'll be looking at CSAT, which is the Computer Science Aptitude Test for some universities that require it, some good universities in the UK. And we'll be talking about other things like game theory, a little introduction to neural networks, Monte Carlo simulation, that kind of thing. Hopefully it's interesting. It's probably a branch of maths that you probably didn't realise existed or was just computing. But unfortunately we talk about it a lot at A level. So first of all, what is an algorithm? Well, an algorithm is just a finite, but it doesn't mean it can't loop. It may loop over and over again, but it's a finite set of instructions to satisfy a goal or to solve a problem. Okay, that is a terrible spelling of finite. So it's a finite set of instructions. So if there's a finite list, doesn't matter how long they're going for, as long as there is an end and there's a start, beginning, and if you follow the instructions and do the thing, it'll tell you what you need to do. Okay, that's pretty much it for what algorithms are. Now there are a whole host of algorithms out there, and you're more than welcome to have a look online and see what they are. I'm only going to be going through a couple today. Algorithms in general, usually it's just a test of can you read instructions and can you follow them through with some accuracy. Now in the real world you just get a computer to follow the algorithm and spit out some data, especially if the input is from a large data source or a table or something, in the millions or billions. It depends what it is. The point is, when data is too unmanageable for a human to deal with, that's where computers step in. And the whole point of decision mathematics is for the humans to kind of quality assess what's going on, making sure that the computer's following instructions correctly and there's no unexpected results, and what you're wanting the computer delivers because it's been given a proper set of instructions that do what they're supposed to do. Now, I'm going to go through a couple of examples of just some really straightforward algorithms. This one is just literally it's a bit like a recipe. There's various steps. You follow the steps. You do what you're supposed to do, and usually you have a table to the right to keep track of what's going on. The other example I wanted to go through is more of like a decision diagram called a flowchart. And you just follow the flow of it. And there's a couple of key points to that. One, these round circular things, they're pretty obvious. They're just the start and finish point. Now, when we deal with a square box, okay, that's an instruction. That's telling us to do something. Okay, so to compute some value, do something, and so on. And these kind of diamond-shaped boxes, they're questions, or more or less known as decision boxes. Okay, so you're going to have to stop doing something for a second and make a decision. Is a particular value that we've got so far greater than or equal to something? Is something square? And so on and so on. And obviously paths split, and depending on the result, no or yes in this case, you would follow the path around. Okay, so let's just go through a couple of examples then. So the following algorithm produces numerical approximation for the integral blur. And at this point, I haven't really talked about integration or integrals. So this is great because you shouldn't really, well, according to this, I haven't really taught you how to do that yet. But if you're just interested in numerical approximation, and that just means approximating it with a number, because this has a value, then apparently this is one way of going about it. So the steps are: start, okay. Next step, input the values of a, b, and n, okay. And then step 3, and then so on, we do things. And it looks like H, A, B, N, H, C, D, E, F are all numbers. And it looks like all we have to do is add things, multiply things, and so on, which is fine. For the case when a equals 1, b equals 3, and n equals 4, complete the table in the answer book, well, I've drawn it here because it's taken from an exam, to show the results obtained at each step of the algorithm. And part II, state the final output. Okay, so by the way, the final output is output F. So once we've got F and the algorithm is done, then we're okay. Right, fine. So let's get cracking then. So input the values of A, B, and N. Okay, that's the first step. So A, let's do this over here. So A was 1, B was 3, and N was 4. Okay, now just to save time, I'm probably going to get a calculator. Even though these calculators are easy and you could probably do them mentally, I just don't want to get any problems with fractions or anything like that. And if you do have any fractions, it's up to you. You can put the exact value in, you can put it to 4 or 5 decimal places, unless it specifies in the question. So input the values of A, B, and N. Check, done that. H is B minus A over N. So 3 minus 1 is 2, divided by N is 4 is a half. So H is going to be 0.5. C is H over 2. So H divided by 2 is 0.25. Okay, D equals 0. Okay, D is 0. The new D, let D equals the old D plus A to the 4 plus B to the 4. Okay, so 0 plus 1 to the 4 plus 3 to the 4 now spits out the new D of 82. So because D is changed, I'll start in a new row, 82, like that. And then E equals A. Okay, so A was 1, so E is now 1. And then E equals B. Go to step 12. Okay, so if E equals B, does 1 equal 3? No, it doesn't. So I go down again, let D, a new D, equal D plus 2 times E to the 4. Okay, so D is 82 plus 2 times and E to the 4, 1 to the 4. So that is now 84. So let D equal to 84. Go to step 8. Okay, we're now at step 8 again. So let E equals E plus H. So 1 plus H, so that's 1.5. We're now here. If E equals B, is E equal to B? No, 1.5 does not equal to 3, so we'll go on to step 12. Let F, no it's not, so we carry on. Let D, okay, I've got to do that again. So the new D is 82 plus 2 lots of E, well the new E is now 1.5 and that's now to the power 4. So that's going to give a new value of 92.125. And then go to step 8. So step 8 says let E equals E plus H. So we're going up again. So 1.5 plus 0.5 is 2. And then if if e equals b, no, 2 does not equal 3. So the new d is the old d, which is 92.125, plus 2 lots of e, which is now 2 to the power of 4. And this is now going to give 124.125. Go to step 8, e equals e plus h. So I add another 0.5 to there, so that's 2.5. And now, where are we? If e equals b, well 2.5 doesn't equal 3, so we stop, carry on. So d equals d, which is that, 124.125, plus 2 times by e, which is 2.5 to the power of 4. Okay, and this will result in 202.25. Okay, then go to step 8. So now e is e plus h. So 2.5 plus 0.5 is 3. If e equals b, does e equal b? 3 does equal 3, so go to step 12. F, the new value f is c times d. Okay, so I need to do 0.25 times by that 202.25, and I will get 50.5625. Stop. Complete the table in the answer book, which I've done. State the final output. The final output is 50.5625. Later on, when we do integration, we'll have a check and see how accurate that was. But essentially, it's not particularly difficult. You just have to follow the instructions carefully. Maybe I've made a mistake. I don't think I have numerically because I used a calculator. But just follow the instructions, just lay them out very carefully, and I'm sure you'll be fine. Okay, the next one. An algorithm is described in the flowchart in figure 2. So there's figure 2, it's a flowchart. We start at the top, flow to the bottom. Okay, part A. Complete the table, recording the results of each step as the algorithm is applied. You may not need all of the rows. Give the values of A, B and C, D to 3 decimal places and the values of E to 1 significant figure. Okay, so first of all we're going to let n equals to 0. Okay, we'll do that. So n is 0 and A is root 5. Okay, so root 5 is to 3 decimal places is 2.236, and B is the negative of that, so it's minus 2.236. Okay, so the first thing we do is let n equal the old n plus 1. So now n is going to be 0 plus 1, which is 1. And now let C equal A to the n to 3 decimal places. I should put the 1 there. Okay. So, well, no, I can keep it like that. It's absolutely fine. C is now A to the n to 3 decimal places, so they're going to be exactly the same because to the power 1 doesn't change anything, so that's 2.236. And D is B to the, so that's minus 2.236. And let E equals C minus D to 1 sig fig. Well, if I do one minus the other, I'm going to get positive 4.452. But E is to 1 sig fig, so 4.4 is going to be approximately 4. Okay, output E. Next up, is n greater than 3? No, it's not, because n is 1. So if I go back, let n equals n plus 1, so I'm now adding 1 to n, so it's now 2. Let's C equal that. Okay, so I need to do that squared. Well, that's easy because it was the square root of 5, so when I square it, that's just going to become 5. Then similarly, minus root 5 squared is also going to be positive 5. And then E is C minus D, so the answer is going to be 0. Is n greater than 3? No, it's not, because it's 2. So I'm going to go back and I'm going to make n bigger. So now I've got to do n plus 1, so it becomes a 3. C is now a, but now cubed. Okay, so I've now got to cube a. So I'm going to cube a to the power 3. And that will give approximately 11.179. Does it? I have to use the 3 sig figs thing of a. Okay, so 2.236, and I cube that. Yeah, if you cube root the a, which was to 3 decimal places, then that is 11.179. Yep, true. Calculator, if you use the exact square root of 5, I think is 11.180. And d, well, the corresponding d value is just going to be the negative of that. So the output will be 1 minus the other, so I times that by 2 to one significant figure, 22.35, and so on is going to be 20. Is n greater than 3? No, it's not. So we loop back round, n gets added to 1, so it's a 4. We then, to the power 4 of 2.236, which is 24.997 to 3 decimal places. Because it's to the power 4, this is going to be the same, so 24.997, because when you raise a negative number to an even power, it becomes positive, so negative root 5 to the power 4 is going to be the same as positive root 5 to the 4. And I'll subtract 1 from the other, that's 0. And then, is n greater than 3? Yes, it's 4, so yes. And we stop. Okay. So, if the restriction n is greater than 3 is changed to n is greater than 100, state the value of e when n equals 100. Well, what's going on here? Well, to me it looks like whenever n is even, the answer for e is 0. And you kind of see why that's going on, because when you take an even power of a positive or negative number, they both become positive, but if you take an odd power of a negative number, it's still odd. And in this line here, we're subtracting the difference. So clearly, if you're subtracting the negative form of a number, once you've raised it to the even power, you're just subtracting the result from itself. So you're going to result in 0. So the end result, when n equals 0, what is e? Well, that's just clearly 0. That's not particularly difficult. Yeah. A little closing point to do with that is you may be asked to scale things up. For example, you might be asked to work out whether, or to state whether an algorithm is non-linear or linear, or the power or the order of an algorithm. Here it's just non-linear. Well, to the power n is not linear, but the actual building blocks as we're going along is pretty linear. You can see the outputs clearly oscillate between numbers backwards and forwards. But the main thing I'm trying to talk to you about is if an algorithm has got a rate and there's an amount of time or steps for an algorithm, and the order or the complexity is some function of n. So where n is the order, or rather that's the input. So you're probably thinking, okay, so what's going on here? The rate for an algorithm is just going to be the time per the order. So the time for something to do n things over some function of the order is going to be the same as if we were to scale it up, so maybe a different input to the m. So if I just bracket off this thing, let's give an example of what's going on. Let's suppose I've got an algorithm that tells me to search an n by n grid. So let's say it's of the order n squared. Well, let's not use n. Let's use x squared. And let's suppose that it takes 2.5 hours to scan a 1 by 1 grid. So clearly the total time here for when it's a 2 by 2 grid is 10. So the question is, what would happen if it was a 10 by 10 grid? What would the time be there? Now you could probably just draw it out and just go, well, I've got, 10, so I've got 100 at 2.5. So yeah, you could probably work it out that way and do it the long-handed way. The other way is to say, well, because I've got t2 over, now the function is the squared function here because I'm creating a square. This will be over 2 squared. This will equal t of 10 over the 10 squared function. Yeah, do you see what's going on there? So t2, I know what that is. That's just 10. So what's going on here is if I times by 10 squared both sides, then t10 is 10 times 10 squared all over 2 squared. And 10 times 10 squared is 1,000. 1,000 over 4 is 250 hours. And it's what you'd expect it to be, because there'd be 100 squares and it'd be 2.5 hours per each square, so it'd be 250 hours. The reason I've done this simple example is because sometimes the function, right, of the complexity or the order of the algorithm might be something really weird. It might be log of n, or it might be e to the n, or it might be n to the power n, or it might be n to the 2n minus 1, and so on and so on. And you don't know the complexity of each algorithm, i.e. what is the function of the order of which the time increases. And being able to have this result to scale up the processing time and figure out how much time a computer would need to solve the similar problem but just scaled up in complexity is really important. So in terms of algorithms, you might be asked to comment on the order, but more importantly you might be asked a question on the rate, or rather the time taken to scale up a problem, whether it's feasible. For example, if a certain algorithm is of order, let's say n cubed, and for 10 iterations it takes 2 hours, then if you've got a problem that needs 400 iterations, can that problem be solved in a month? That kind of thing. So you're scaling things up. Okay. Right, sorting algorithms. So let's actually get to the bread and butter of it. So now, what can I say about this? Well, the problem with this is there's not just a set amount of sorter. Well, there are, but I mean, for the edXL course, there's a few that you need to know off the top of your head. But unfortunately, computer scientists have made tons and tons and tons of algorithms. And if you want to explore that, that's absolutely fine. But essentially, if you understand one or two, then you know how to apply others as well. And it's just, essentially the decision part of mathematics at A level is just memorizing a bunch of things that you need to, and applying it. There's no complexity to it other than that. So there's a couple of algorithms that you need to know. So for these demonstrations, I'm just going to use this same set of numbers. Okay, and there's a couple of sorting methods. And what do I mean by sorting? I mean, I want to put them in ascending or descending order. What does that mean? Well, ascending order means I want the smallest first, and then going from left to right, they get bigger and bigger. And descending, descending means we start with the largest one and we get smaller and smaller. To be fair, the steps for ascending or descending are very similar. If you've ordered the list and it's in descending order and you want it to be ascending, you just swap the whole list over. That's not difficult. So let's start with a quick sort. Quick sort. Okay, how do we get things in order using a quick sort? So here's my numbers. So how does a quick sort work? Well, the quick sort, essentially let's write the steps over here. Maybe I shouldn't have done that. So steps to a quick sort is you identify a pivot number, and I'll talk about that in a second, and it's in the middle of all sets of numbers. Now there will be multiple sets of numbers because you're going to be splitting this up into various bits. 2, you're going to rearrange in order from left to right. That doesn't matter. I mean, you could do it from right to left, it doesn't matter. But the numbers either side of the pivot, but keep the relative positions the same. And then step 3, repeat and go back to step 1 if not in order. Okay, so there's a couple of terminologies here. Doing this whole thing once is called a pass. Okay, and every time we compare two numbers, so we'll call that a comparison, we use this little like underline thingy. So if I wanted to compare, say, if I wanted to compare 12 and 18, I'd do a little line like that. And if I had a comparison and I wanted to swap numbers, it would be a line and then a thing through it like that. We're not going to use it for this algorithm, but we will be doing in a second. So, okay. By the way, to find the pivot, you always do the number of numbers n plus 1 over 2 and always round up. Okay, so it's not a case of rounding to the nearest one, you always round up. Okay, so let's do the first pass. So this is the start. Okay, so how many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8. So 8 plus 1 over 2, and then rounded up. Well, 8 plus 1 is 9, 9 over 2 is 4.5, 4.5 rounded up is 5. So 1, 2, 3, 4, 5. I'm going to call this one my first pivot. And I like to draw geometric shapes in terms of numbers of sides. So the first pass, the smallest geometric shape, or rather the shape with the fewest amount of sides, is the triangle. And then for the next pass I'd use squares, and for the next pass I'd use pentagons, the next pass hexagons, pass after that heptagons. Or I could just draw a funny shape and put a little 7 above it, it doesn't matter. Usually the lists are quite small because you're not computers, but you know, for the purposes of this, it'll be fine. Okay, so what would my list look like now? So this is 30, I've drawn a triangle over it. Okay, now step 2, rearrange in order left to right numbers either side of the pivot but keep the relative positions the same. Okay, so what does that look like? Well, we start from the left hand side, 75. Is that bigger or smaller? I should have clarified, we want to make this ascending in this case. I mean, if it was descending, you probably get the gist of it, but let's go for ascending. So we want the smallest to biggest. So is 75 smaller or bigger than 30? It's bigger, so I'll put that first on the right hand side, 75. Is 100 bigger or smaller? It's bigger, so that's next along. And notice how 100 is to the right of 75. We haven't made comparisons about 75 and 100 yet. We don't know if that's correct. Is 52 bigger? Yes, it is. That will go to the right. Is 92 bigger? Yes, it is. That goes to the right. Might have to move all this over. Next up, 84 is bigger, so put that to the right. 42 is bigger, so put that to the right. And 60 is bigger. So here we've done one pass. We've compared all the numbers, and it looks like it hasn't really done much. All it's done is sorted 30 to be the lowest one. So this is the end of the first pass. Okay, now let's look at the subset of numbers. 1, 2, 3, 4, 5, 6, 7 numbers there. There's only one subset. So we're going to do the 7 plus 1 over 2 rounded up number. Well, 7 plus 1 is 8 divided by 2 is the fourth number. So we take the fourth number along, 1, 2, 3, 4. So this is now my new pivot. So keeping this exactly the same. This is going to be my second pass. So if 92 is my pivot, here it is. Okay, is 75 bigger or smaller? Well, 75 is smaller, so we keep it to the left. Is 100 bigger? Next one along. Yes, it's bigger, so we put it there. Is 52 bigger or smaller? No, it's smaller, so I keep it to the left. Is 84 bigger or smaller? It's bigger, so I'll put it to the left. And kind of see the numbers as like stacking. Move this over a little bit. Where are we? 42, that's smaller, so I'll stack it to the left. 60, bigger or smaller, that's smaller, so stack it to the left. So at the end of the second pass, the list of numbers looks like this. Okay. How are we doing for space? Yeah, loads of space. Okay. For the third pass, let's use orange now. So there's actually two sets of numbers now. There's this set of numbers and there's this set of numbers either side of the pivots. So for the right hand side, this is clearly going to be its own pivot because there's only one number in that subset. But on this side, there's 1, 2, 3, 4, 5 numbers. So 5 plus 1 over 2 and then round it up. Well, 5 plus 1 is 6 over 2 is 3, so it's the third number, 1, 2, 3. So 84 is the new pivot of this set of numbers. So let's do this again. So what would the next list look like? Well, these need to be deleted. Okay. Is 75 bigger or smaller than 84? It's smaller, so I'll put it there. Is 52 bigger or smaller? It's smaller, so I put it to the left. It stacks to the left. Next up, is 42 bigger or smaller of that pivot? It's smaller, so I stack it there. Is 60 bigger or smaller? It is smaller, so I need to stack it here. Okay, now that's done. And now this is the end of the third pass. Okay. Next up, I just have one list of numbers. There's 4 here, so you know the drill by now. 4 plus 1 is 5, over 2 is 2.5, rounded up is 3. So what's next? A hexagon. Let's go for brown. So third number, doosh, 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 doosh. That's my pivot. So same deal again. By the way, if you're probably thinking like, oh, this is so useless, like why are we doing this? I can clearly tell what numbers are ordered which way. And my response to that is like, yes, you should blooming know what the numbers are, ordered as. But the point is, you've got to think of this as like a set of instructions that a computer can follow. So numbers either side of the pivot of 42. Well, 75 is bigger, so I stack it to the right. 52 is bigger, so I stack that to the right. And 60 is bigger, so I stack that to the right as well. Okay. Okay, let's spread this out a little bit maybe. Okay, so the end of the fourth pass. We're nearly getting there actually. If you look at the bigger picture, we've got the two smallest numbers in the correct order, and we've got the three biggest numbers in the correct order. We just have to worry about this stuff in the middle. So let's go for blue. There's three numbers here, so 3 plus 1 is 4, over 2 is 2, so it's the second one. So heptagon, it's like that, whatever. 1, 2, 3, 4, 5, 6, 7. Oh, yeah, it's just not. It's an irregular heptagon. Okay, so let's get these things in order. You don't have to be so elaborate with this is the end of the fifth pass. You don't have to be so elaborate with where you put or how you define. To be honest, you could just underline the pivot like that of the next row and make it easier. It doesn't matter. I just like doing it with shapes just to illustrate a point, and because I'm using a bit of hardware and software. But if you're in an exam and using pen and paper, it's probably best to just keep a track with a line under it. So 52 is there. Start from left to right. So 75 is clearly bigger. So 75 will go here, and then we've got 60 to compare, and that's still clearly bigger. Okay. So next pass. Still not in order. So there's only two numbers. So 2 plus 1 is 3. 3 over 2 is 1.5. Round that up is the second one. So let's just go for a circle now. Let's have it green. So the sixth pass will be 60. Oh dear, that's terrible. I can write. I am literate. Sixth pass. Okay, so if there's 60, then clearly 75 is bigger, so these are going to actually swap positions. Okay, now we've just swapped them, but we haven't actually done the check to see if they're ascending. So for the seventh pass, there's only one number left, so that'll go its own, it's supposed to be a star, terrible star. That will get its own pivot, and then therefore, because every number has now been a pivot at some point, we are now fairly confident that these numbers have been put in ascending order. Okay, so it doesn't seem like that was a particularly quick sort, but this actually works with this actually works really well for a large amount of numbers. Why is that? Well, if you look at the original thing, we're a bit unlucky really, because every time, okay, if you've got a bunch of numbers, if you've got a bunch of numbers, say there, and you pick the middle point of one number and you jiggle them around so that there's roughly half on that side and roughly half on that side, you need to expect on the next pass that of each subgroup there'd be a half point there and then a half point there, and then you jiggle them around, so roughly half on that side, roughly half on that side, and then on the third pass you'd pick the middle number of this group, 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 and you'd keep going, and you're subdividing the sets in two each time. So after 7 or 8, 9, 10 subdivisions, you should have broken down a group into about 1,000 sets. Here we're a bit unlucky because every time we were subsetting numbers, it was only really, I mean, for example, if you look at the first one, 30, that pivot happened to be the lowest number. So then for the next pass round, we just had all the numbers to the right. So we only had one pivot for the second pass. And then for the third pass, because 92 was the second largest one, the group on the right was almost like a trivial group because it was its own group. So yeah, it's just the way it goes sometimes. But this is a quick sort. It's one of the ones you need to know. I'm going to make this a little bit bigger to leave some space. So let's make this. Can I do this? Yeah, boy. Okay. So next up, I'm going to look at another algorithm, and I'll do a different color. It's referred to as the bubble sort. You can either, the reason it's called bubbles is because you can, well, as I said before, you can either compare two numbers like that, or you can put a bubble around the two numbers like that to show that you compared the two numbers. That's the only reason it's called the bubble sort. It's nothing particularly fancy. But essentially, what you do is, the first step is you compare the numbers left to right, one pair at a time. Second, you swap if necessary, and then move to the next pair. And then when you reach the end, go back. Side note, if a pass required no swaps, then you're done. Okay, again, I'll go through the example up here to show exactly what I mean. Some people like this one. You might say, well, hold on, why is the other one called the quick sort if this one's quicker? No particular reason. The problem is with this works well with small sets of numbers, is because essentially this algorithm, you go through the whole set every pass, whereas the quick sort, you're splitting them down into subsets, and you're making the sets you need to check a lot smaller each time. So for small sets, this might seem like a good idea, but it doesn't scale up particularly well. Okay, so let's do this. So let's keep a track. So this is the start. Then a question might be, how many passes does it require to go through a quicksort? And my answer there would be, at the end of the 7th pass, the numbers were in order. You could probably say the 6th, because you've chosen the pivot as 75, but you have to go through a sweep of the whole numbers and make sure that there are no numbers left to compare or move in order for the algorithm to finish. So you've always got to finish with a check, just like your work should really. Okay, fine. So let's do this. So 70. So let's say we're going for, well, what did we do last time? Did we do ascending or descending? We did ascending. So I don't know. For giggles, let's do descending this time. See how that works out. So 75 and 100. So that means we want the bigger ones to the left, and we want the smaller ones to the right. So is 75 bigger than 100? No, it's not. So I'm going to swap. Okay. So then, so what I'm going to do is I'm going to move that 75 over and swap it with the 100. And now I compare 75 and 52. Is 75 bigger than 52? It is, so we leave 52 alone. And you kind of cascade, well, just see what I'm going to do. You cascade down. So I don't have to worry about 175, 100 and the number 75, because they're gone. They've been compared. I'm never going to go back to them. So 52 and 92. Are they in the right place? Well, no, 92 needs to be the left of 52. Then bring the 30 down. 52 and 32. In descending order, that's fine. So then we'll move on. Really, I should have done it like this to save space. You should only really need a new line when you're doing a swap. So 52 and 92, that's swap. So 92, 52. So that's been compared and swapped. 52 and 30, no, that's fine. 30 and 84, or 84 is bigger, so that needs to go over there. 30 and 42, that's bigger, so 42 and 30. 30 and 60, that's the swap, so 60, 30. And now once you've done that, you can actually look back and see. So that should have been 42, that should be 84, that should be 52, that should be 92, 75, 100. So actually this is the set of numbers after the first pass. Okay, and now we're going to do the same thing again, and we just keep going. And notice how I made 1, 2, 3, 4 switches. 5 switches during the first pass. Okay, and that's why the notation of comparisons and switches is probably quite useful here. So 175, no, that's fine. 75 and 92, that needs to be switched. So 92, 75. 75, 52, that's fine. 84, no, 84 is bigger, so that's switched. 84 and 52. 52, 42, no, that's fine. 60, no, 42 and 60. 60, 42. 42 and 30, that's fine. So now the next list will be 52, bring the 84 down, 75 down, 92 down, and 100 down. So I'm just bringing these numbers down into their slots. So now we've got this set of numbers, and this is the set of numbers after the second pass. And because we made 1, 2, 3 switches, we're going to have to do it again. When we go through a pass and we don't make any switches, then that means we're in the right order. So let's go again. 192, that's fine. 92 and 75, that's fine. 75 and 84, that's not okay. 84 and 75 need to switch. 75 and 52 is fine. 52 and 60, that's not fine. So 60 and 52. 42 and 52 are fine. 42 and 30 are fine. So the new list becomes 75, 84, 92, 100. So this list there is now after the third pass. And because I had to make 1, 2 switches, I need to carry on. And hopefully you're getting the idea by now. So 192 is fine, 92 and 84 is fine, 84 and 75 is fine, 75 and 60 is fine, 60 and 52 is fine, 52 and 42. Really, I should have, hold on. How am I going to do this? Yeah, I've been a bit slack here. I mean, really, and I've been incredibly lazy here. Apologies. But then 52, 42, and 30 will be fine as well. So because there is no comparisons, there's comparisons, but there's no switches. Now this algorithm has set these numbers out in descending order. And if you notice, it is the same as the ascending one, but just reversed the position. Okay, so yeah, that's pretty much it in terms of sorting algorithms that's on the course. There are a couple that used to be on the course for Edexcel Further Maths, but aren't anymore. I mean, I'm quite happy to talk about what they are, but another one, as a little side note, is the binary search. And it's not really a sorting, it's more like finding a particular thing. So a binary search is, say you've got a list of numbers, or list of something, objects, let's say A, B, C, D, E, F, and they're ordered already, then it's a very similar thing. What you do is you pick a pivot, which is m plus 1 over 2, and then round it up. And then you delete either side of pivot until you find. And you found it when the object becomes the pivot. So let's say from this example I want to find the letter D. So there's 1, 2, 3, 4, 5, 6. 6 plus 1 over 2 is 3.5, rounded up is 4. So I'll make 1, 2, 3, the fourth number the pivot, and I've found it. So the algorithm stops. Let's suppose instead of D I want to find the letter B. And this seems trivial because when it's just a small set like 6, you can go, oh, it's there. But if it was larger, and we're talking about databases with millions, billions of objects, then same deal. How many objects are there? There's 6 plus 1 over 2, which means we're going to be dealing with the fourth object, which is D. And then we say, right, is B before or after everything in the alphabet? So it's before D, so we delete everything including D before the alphabet afterwards, because we know it's not in there. It's not the pivot and it's not after it, so we can delete everything. And then of this smaller subset, there's 3 things, and now we repeat the process. So there's 3 objects plus 1 over 2, so that means we're going to make the second object the pivot. And in this case, the second object is B, and because B is the pivot, then we found it, so we stop. And if it wasn't the pivot, then, you know, let's suppose we were looking for A. Then because A is before B, we need to delete everything after B, including the pivot. So we're left with A, and then the next pass there's 1 object, so 1 plus 1 over 2 rounded up is 1, so we'd make A the pivot, and then we found it because it's the pivot. It's not in the spec anymore, it's pretty easy to pick up. Yeah. The final bit that I want to talk about before I do some examples, and I'll leave it there, is stuff called bin packing. Okay, and we're literally going to pack things into bins. Now, let's suppose I've got my set of numbers here. Let's make them smaller. And let's suppose I've got those numbers and I want to pack them into bins. Literally putting them into containers, and the containers have a fixed amount they can store. And for this example, let's say they can hold 120. So I could, if I wanted to, fill this bin up with a 75. I could fill this bin up with 100, so there's 20 left. I could fill this bin up with a 52 and a 30, which is going to be 82. Probably not a great idea, but I could, and so on. Then these types of questions are to do with what's the optimal or the least amount of bins I would need to hold all of this data. And there's three ways of approaching this question. Well, there's 3 ways we'll talk about. The first one is the first fit algorithm, and that's when you take the unordered data and you just fill up the bins systematically and then move on to the next bin. So what does that mean? So let's take our example. So first one, 75. We'll put that in the first bin, 75 there. So that's done. Next number, 100. Well, we can't put it in the first bin, so we need a new bin, so we'll put the 100 there. Next, 52. So we put the 52 in a new bin because it can't fit in any of the others. Next, 92. Well, I can't fit 92 in any of them going from left to right, so I need a new bin for 92. 30. Well, I can fit 32 in the first bin, so I'll put 30 there. 84. I can't put it in the first, I can't put it in the second, I can't put it in the third, I can't put it in the fourth, so I'll need to put it in the fifth. So there's my 84, sorry. 42. Well, I can't put it in the first or the second, but I can put it in the third. So that's now 94. And 60, well, I can't put it in the first, the second, the third, the fourth, the fifth, so I'll need a new bin. So there's my 60, capacity of 120. So as you'd expect, it's not particularly efficient, this method. There's lots of gaps, little gaps in all of the bins, and you might be wondering, is there a better way of more efficiently packing the bins than this? And usually the first fit method is pretty inefficient. We'll be looking at another method, and that would be first fit decreasing. So first fit decreasing is exactly the same as before, but you put the list in descending order, and then you do the first fit algorithm. So this one, in this case, took how many bins? 6 bins. It's not great. So let's get rid of all this. Okay. So let's get these numbers in descending order. And I've done that already. That's 100, 92, 84, 75, 60, 52, 42 and 30. So let's do first fit decreasing. So here's my bin of 120, so I can whack 100 in there, that's totally fine. Next up, let's get a couple of bins here. Well, we just did the other one in 6 bins, so the worst, we can't do any worse than 6 bins, surely. Next is 92, we're going to need a new bin for that, so that's fine. Next is 84, yep, we'll need a new bin for that, it's totally fine. 75, yep, afraid so, we're going to need a new bin for that one as well, moving from left to right. 60, yeah, we can't fit it into the first 4 bins, so we're going to put it in the 5th bin, that's fine. 52, right, well, we're going to have to put it in this bin, 52. So now that one is 112. 42, no. 75 plus 42. Oh, I think that'll just fit, won't it? 40 plus 70 is 110. 2%. Pardon me. So that's 117. So that's fine. And then 30, I believe, can fit in this bin here. That makes 114. So actually, we've already made a bit of an optimization, because we did 6 bins with the first fit, but now with the first fit decreasing, we can fit all of the stuff into 5 bins, so we don't need as many bins. The third and final method is what's called the full bin packing. And this method, you kind of visually see it, but you try and create full bins first. Okay, you try and like completely fill up a bin first, as optimally as you can. So what would that look like over here? Well, let's get rid of all these liney things. Is there a way? Well, most we've needed so far is 6, but we know we can do it in 5. Okay, let's have a look. Well, 100, let's write down what they need. So 100 would need 20, 92 would need 28, 84 would need 36, 75 would need 45, 60 would need another 60, 52 would need 68, 42 would need 78, and 30 would need 90. Okay, well, there's no 20s, there's no 28s, there's no 36s, there's no 75s, but 75 and 42 would be pretty close. That would be 3 away from a perfect bin. So 75 and 42 would be 3 away from a bin. Where else would we be? Well, I think the next closest from inspection is 84 and 30, because that would be 6 away from a bin. So 84 and 30 would be 114, so that'd be 6 away from the bin. 52 and 60 would be 8 away from a bin. So what are we left with? So that's gone, that's gone, that's gone, that's gone. So really there's 92 and 100. Well, that's just left on their own, right? 90, 100 and 92. So we try and fill up the most tightly packed bin as possible. So the first one had a gap of 3, the next one had a gap of 6, the next one had a gap of 8. I don't think we could have been more optimal there, and then so on. The next question is, well, this could be done in 5 bins. The next question is it even, what's the optimal upper bound? Or lower bound, sorry. Like, is it even possible to do it in 4 bins? And the way to check is what you do is the lower bound, I'll call LB, is going to be greater than, and then what you do is you sum up the data and you divide by the capacity of the bin. So in this case we're going to need to add 75 plus 100 plus 52 plus 92 plus 30 plus 84 plus 42 plus 60, which is 535, and I divide that by 120, and my lower bound has to be greater than 4.4583 recurring bins. So I can't have it on 4 bins. It has to be the next number that's greater than or equal to 4.45. Well, you can't have 0.458 of a bin. So the first number that's bigger than that is 5. So really, any packing in this example where I can do it in 5 bins is optimal. I can't get it better than 5 bins. So that configuration is optimal. And that's pretty much the basics of some sorting algorithms, bit of bin packing. Well, let's talk about some advantages. The first fit algorithm, I mean, it's really dumb. I mean, one of the pros is it's really easy to do. You just bang everything in. You take the first object, put it into the first bin, take the second object, try and put it in the first. If that fails, put it in another one, and then so on and so on. Bad points of it is, well, it's, as we saw, it's just, there's no rhyme or reason to it, and generally speaking, it's not particularly good or efficient. So easy to do, but not particularly good. If you just want a solution, you don't care about the waste, then fine. First fit decreasing is pretty good. I mean, you can see how we got the optimal solution in 5 bins, and it's fine. I mean, it might not give an optimal solution. It is fairly easy to do. Downsides would be you've got to order the list first, and that might be additional computing time and so on. But if it's already done for you, then you should be fine. And then for the full bin packing, it is pretty much the optimal solution because you've defined it to be that way. You're trying to fill up boxes before moving on. Disadvantages is not particularly guaranteed to be the optimal solution. And as you saw before, a lot of it is just by inspection. It's not particularly difficult to do. It's not immediately obvious which ones are bigger or which ones, compare to make optimal bin packets. It's difficult to program for because essentially you're doing lots of comparisons and subtotals and so on as you're going on. It's just not great in general, but it does tend to yield better results. Okay, now it's the point where I'm going to do some examples, and again, if you want to try it yourself, you're more than welcome to pause the video and give it a go. I'm just going to grab a drink. Okay, so question 1. Use the first fit bin packing algorithm to determine how many numbers listed above can be packed into bin size of 5. Okay, so 2.1 can be fitted in, that's not a problem. So that's done. 1.7, well 2.1 plus 1.7 is 3.8, so that can be fitted in right there. So we've now got 1.2 left. 3.0 is going to need a new bin. 1.9 can be fit into that bin. It can't be fit into the first because it only got 1.2 left, so this has got 0.1 left. 3.2 will need a new bin, which leaves 1.8 left. 1.2 can be fit into the first bin, so that's full. 3.3 needs a new bin. 1.4 can be fit into the third bin if we're going from left to right, because the first bin's full, the second bin's got 0.1, so that will make 4.6. 1.5 would have to go in the fifth bin, so it's now 4.8, and 0.2 would go in the fourth bin, I believe, because that's 4.6, so that'll be 4.8. So there's 0.2 left over there, there's 0.2 left over there. Okay, so use the first fit bin packing algorithm to determine how the numbers listed above can be packed. Okay, did it now. The list of numbers is now to be sorted in descending order. Perform a quick sort on the original list to obtain the sorted list. You should show the result of each pass and identify your pivots clearly. Oh god. Right, okay, so this is for my part A. For part B, I've got to do 2.1, 1.7, 3.0, 1.9, 3.2, 1.2, 3.3, 1.4, 1.5, 0.2. Okay, so for the purposes of this, I only have to show the results of each pass. So hold on, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 plus 1 is 11, over 2 is 5.5, round up is 6. So 1, 2, 3, 4, 6. So this is my pivot. And what I'm going to be doing to save time is when I choose pivots of that pass, so I'll call this the start. When I choose pivots of that particular pass, I put a square around it, and when I've made it so that they were pivots and they're not pivots anymore, I'll just put a line under it just to save time. So 2.1 is larger than 1.7 and 3, so I'm pretty sure everything apart from 0.2 is bigger. So I'll just rewrite the list out again. 0.2, 1.2 is the old pivot, underline it. And then I'll do 2.1, 1.7, 3.0, 1.9, 3.2, 3.3, 1.4, 1.5. So the relative positions haven't changed, but all the stuff that's lower. Okay, fine. Next up, this is its own pivot for the first end of the first pass. And then there are 1, 2, 3, 4, 5, 6, 7, 8 there. So 8 plus 1 is 9. Fifth one, 1, 2, 3, 4, 5. So that's the new pivot here. So 0.2 is the old pivot, that's done. 1.2 was a pivot, so that's done. So 3.2, so 2.1 was smaller, 1.7 was smaller, 3.0 was smaller, 1.9 was smaller, 3.3 was bigger, 1.4 was smaller, 1.5 was smaller, 3.2 was an old pivot, and 3.3 is on its own. So this is the end of the second pass. So there's two subgroups now, 1, 2, 3, 4, 6 in the middle, 6 plus 1 is 7, over 2 is 2.5, is 4, 1, 2, 3, 4. So that will be a new pivot, and 3.3 will be a pivot on its own. So for the next pass, we'll have 0.2 has been a pivot, 1.2 has been a pivot, And then 1.9, the only ones smaller are 1.7, 1.4, 1.5, and then 1.9 was a pivot, and then we've got 2.1 was bigger, 3.0 was bigger, 3.2 was an old pivot, and 3.3 is an old pivot. Two groups, I've got 3 there, so this is the end of the third pass. By the way, it wants descending order. I know I'm doing them in ascending order, but the last step can just be to swap all the numbers over. Of 3, 3 plus 1 is 4, 4 over 2 is 2, so that's going to be a new pivot. And then 2 plus 1 is 3, 3 over 2 is 1.5, round up, so that's a pivot. So then it's going to be 0.2, old pivot, 1.2, old pivot. 1.4 is smaller than 1.7, 1.5 in that order. 1.9 was a pivot. 2.1 stays where it is. 3.0 is a pivot. 3.2, 3.3. That's the end of the fourth pass. Dear me, 1.4 is an old pivot. Now this is a subgroup, that's on its own. 1.7, 1.5, 2 plus 1 is 3, over 2 is 1.5, rounded up, so it's 2. So we're going to have 0.2, 1.2, 1.4, 1.7 is bigger, so 1.5, these are all old pivots. 1.7 is there, 1.9 old pivot, 2.1 is an old pivot, 3.0 old pivot, old pivot. Everything's an old pivot. Okay, so this is the end of the fifth pass. 1.7 is the pivot. So then now we're going to have 0.2, 1.2, 1.4, 1.5, 1.7, 1.9, 2.1, 3.0, 3.2, 3.3, and they've all been pivots. So at the end of the sixth pass, they've all been pivots. So now we just have to swap the order. So it's now 3.3, 3.2, 3.0, 2.1, 1.9, 1.7, 1.5, 1.4, 1.2, 0.2. And now at the end of the sixth pass, we now have a sorted list. Oh, sweet Jeebus. I'm just going to make this smaller. Okay, so that was my part B. Oh, that was my part B. Okay, for a list of n numbers, the quicksort algorithm has on average order n log n. Interesting. Okay, so that's my order. So that's my function of n, right? Given that it takes... Okay, fine. So given that the time for n over the function n, this will equal the time for the new thing over the function of the new thing. Okay, so given that it takes 2.32 seconds, so 2.32 seconds over n of 450 of that function, so 450 log of 450, this will equal the new time that we're interested in, and oh god, it's now to the power of 11250 log of 11250. So the new time is going to be 2.32 times 11250 log of 11250 all over 450 log of 450. Yeah. So calculator check. So fraction 2.32 times 11250 log of 11250 over 450 log of 450 will give approximately 88.56 seconds. So what does that mean? For a list of n numbers, the quicksort algorithm has an average order n log n, where n is the number of things. So if it takes 2.32 seconds to run the algorithm when there's 450 numbers, calculate how long it would take to the nearest tenth of a second. Ah, So 1/10 of a second, 0.56 would round up to just 88.6, wouldn't it? 56 rounds to 88.6. So when there's 11,250 numbers, we're approximating it would take roughly 88.6 seconds. Now, logarithms we talked about a little bit before. Essentially, the log button is the same. Well, the log function is when you write it out as log, log, then what we're saying is log of base 10. So if you do log 10 of 10, it should output 1. You can check this on your calculator. Log of 10 should just give 1. If you do log of, say, 100, then it's log base 10 of 100. And that's essentially saying 10 to what power is 100, so that's 2. And again, if you use the log button and then 100, that should verify it for yourself what's going on. I did talk about logs briefly, and I'll be going over more of them in the number and algebra stuff. But essentially, that's what you need to do for part C. Okay, next question, home straight. So, the list of numbers is to be sorted in descending order. Perform the first pass of a bubble sort, giving the state of each list after each. Okay, bubble sort. So, for part A, I've got 25, 22, 30, 18, 29, 21, 27, 21. The first pass, I want it descending order. So 25 and 20 is fine, 22 and 30 is not okay, so I'll swap them over. 22 and 18 is fine, 18 and 29 is not okay, so 29, 18, bring the 21 down. That's not okay, so 21, 18, 27, that's not okay, 27, 18, 21, that's not okay, 21, 18. So after the first pass, it looks like this. So that's after the first pass. So that's my answer for A, and then AI, sorry. And then for AII, perform further passes given the state of the list after each pass until the algorithm terminates. So, okay, so I'm just going to state these without doing the thing. You can probably see what's going to happen actually, and this is perfectly fine. If it tells you, you only have to state them. Well, 25 and 30, they'll swap, so that's 30 and 25. 25 and 22 won't swap, so 25's there. 22 and 29 will swap, so 22 and 21, 22 will be there. 21, 27, so 27 swaps. 21, they're two 21s. Have I written that down properly? Lol, what's going on here? Yeah, there are two 21s. Jeez, okay, fine. So then this becomes 21 compared to 21 is fine. They don't swap. 21 and 18, that's fine. Okay, third pass. 30 and 25 is fine. 25, 29, 29 swaps. 25, 22, that's fine. 22 and 27, 27 swaps. 22 and 21, that's fine. So now they're all just going to be fine. Fourth pass. 30 and 29, that's fine. 29, 25, that's fine. 25, 27, 27 swaps. 25, 22. And then these will stay the same. And then for the fifth pass, we've got 30, doesn't swap with 29, doesn't swap with 27, doesn't swap with 25, and doesn't swap with the rest of them, so we're done. So it will take 5 passes. The fifth pass is there's no comparisons, or there are comparisons, there's no swaps, it's done. Okay, so the algorithm's terminated. Okay, part B, show the result. The numbers represent the lengths in centimetres of pieces to be cut from rods of length 50. Show the result of applying the first fit decreasing bin packing. Okay, so there's the doodah. So first fit decreasing, so 50. So first one's 30, so I'll fill up with 30. Next one's 29, well I'm going to need a new bin for that, so there's 29. Next one's 27, so I'll need a new bin for that, 27. Next one's 22. I can't fit it in the 30. I can't fit it in the 50. I can fit it into this one, 22. So there's only one left over. 21. I can't fit it in the first one. I can fit it in this one, so that's a completely full bin. And then there's another 21. So filling in from the left, it has to be a new bin, 21. And then 18, I can fit it in the first bin, so that's now got 2 left over. So that's not actually that bad actually. There's 2 left in the first one, there's nothing, it's completely full in the second, there's 1 left in the third, and the last one has got a gap of 29. Fairly optimal, I think, just looking from it. Determine whether your solution has a minimum number of 50 centimetre rods. Oh, that's easy. How can we find a lower bound? We just add them all up. So 30 plus 29 plus 27 plus 25 plus 22 plus 21 plus another 21 plus 18 is 193, and I'll divide that by the capacity, which is 50, which is going to be 3.86. So the first number that's above that, because you can't have 3.86 bins, is 4. So any combination where I can do it in 4 bins is totally fine. So yeah, this is one potential. It might not be unique, but this is one potential way. So yeah, it seems optimal. Does seem optimal. And that's it. Thanks very much.